Hey everyone, so I just wanted to do a really quick breakdown of some of the things about the APC that you might need to know. Some of you already taken calculus, so you'll know a lot of the questions that we do. Uh, so, but I just want to show you kind of how it looks when it comes to the APC, like what to actually expect. So first off, I just wanted to run down kind of how the questions or the test is laid out. It is slightly different from the AP1. Uh, Similar to the AP1, it does have two sections. There's a multiple choice section and free response. That's pretty straightforward. And very similar to the AP1, I think in both cases you have about 45 minutes to complete uh, both sections. So you have 45 minutes for section 1, 45 minutes for section 2. This is where it does get a little bit different. For section 1, the multiple choice section, unlike with the AP1 where there was 50 multiple choice questions, here it's going to be 35 multiple choice questions. And also, each one's going to end up having 5 choices. Again, when you actually look at the homework questions, all those AP questions, the ones that have 5 choices, they're actually coming from the APC already. So a lot of you already have experience seeing 5 choice questions. Recall that the AP1 actually is only 4 questions. And then similar to, or again, another difference between the AP1 and APC, the Section 2 free response, here it is only 3 questions long, while in the AP1 it's 5 questions long. So everything is a little bit shorter. A lot of this has to do with the fact that technically there's 2 APC exams that people tend to take together, so they make it a little bit shorter. Just kind of going through a little bit of a breakdown of both sections since this is going to play a part. For the multiple choice, like I said, unlike the AP1, which were very conceptual, tricky questions that kind of relied on experimental situations, here the questions are very straightforward. They're actually, again, straight from the homework questions that we've done. So, they'll straight up ask you what they want. No real tricks. Only about, even though this is the calculus version, I don't want you to think that every question has calculus. Only about a fifth to maybe a quarter have calculus in there. For example, in the practice test that I posted onto Canvas, of the 35 multiple choice questions, I was only able to find 7 questions that either had to use calculus or could be answered in calculus, since you could get away around some of these questions without the calculus, but the calculus makes it a little bit easier. I had to look through a little bit more clearly. Originally, they weren't going to allow calculators for the section 1. I think they've changed it. I looked on to the AP website, and it does say that you're allowed calculators. I just want to double check before I, hardline that in. So just be careful. You might have to remember the reference table. You might have to do a lot of this stuff in your head. I'm not too sure, and I'll get a more concrete answer later on. Section 2 is the free response section. Like I said, there's going to be 3 questions. Now, the really nice thing about these 3 questions is they're always the same, and they're always pretty much asked in the same order. The first question is pretty much a motion question dealing with kinematics and dynamics, so forces and you know the acceleration equation, all that. The second question is going to be some sort of conservation law, so conservation of energy, conservation of momentum. That doesn't mean that this can't, the motion question can include momentum, but it's just that the second question will be focusing more on the idea of, energy is conserved, momentum is conserved, yada yada yada. And then the third question is going to be the rotational motion question. Honestly, the rotational motion can be the trickiest one. Of the 3, only one of them is going to include calculus. So as I've mentioned, you can actually pass the AP exam without doing any of the calculus questions. Though I do recommend that you figure out how to do calculus, only because it is those questions aren't really that difficult. But typically, the motion or rotational motion will tend to have the calculus one. Usually, the conservation law, it kind of stays clean. One of the questions may actually end up being experimental design, very similar to AP1. One thing I wanted to point out though is that these questions are very balanced. If you look into the previous years of free response questions uh, throughout the AP exams, you'll notice that any question where one of them is really tough, then the other two will be disgustingly easy. If all three of them are basically similar difficulty, then they'll be kind of medium difficulty, I guess. A lot of times it's actually nice to have one really hard question and then have the other two being really easy, because then you know you'll at least get a 60%, 60 2/3 of the questions, which means that you're more likely to get a passing, get a 4, maybe even a 5. All right. So I just want to go through what the calculus looks like. That's just what I want to focus in this video a bit. The calculus is very basic, so for anyone who's already taking calculus, this is going to be really easy. Now recall that in the AP1, I've constantly said that the acceleration is always constant, that you'll never have a change in acceleration, yada, yada, yada. APC, that's thrown out the window. The acceleration actually can change over time, and like I said, anytime you're dealing with calculus, it will be changing over time. So don't hardline yourself and put yourself into that acceleration can't be changing. In this case, it can be. You'll need to know the derivatives and integrals of two different things: quadratics and trig functions. Now again, if you're taking calculus, this might be the easy part. You say, okay, I already know how to do that. That's all nice and dandy. I'll run through for those who aren't taking calculus or may not have completed all of calculus. Maybe you're just taking pre-calc. I'll explain to you what a derivative and integral is. I'll do it very quickly. I'm not going to actually do like a whole course on it. If you want a little bit more details, feel free to ask me and I'll go into a little bit more detail. One thing to note, the term derivative and integral is just a really fancy way of saying slope and area. So I just want to point that out because that will actually play a part in a moment. So derivatives are fancy slopes and integrals are fancy areas. Now another thing that you're going to have to do, and this might be actually something that even the kids who are taking calculus may need to brush up on, is how to actually take some of the equations we have and rewrite them in terms of calculus. All right, so a lot of the equations that we actually have, we can actually rewrite into calculus form. Some of them are on the reference table, but you still want to know how we can take, how the normal equations turn into the calculus forms. So for example, some of these you might actually know if you've already taken calculus. So for example, the equation for average speed is d over t, distance over time. We could actually rewrite this as v as a function of time, that's what this parentheses t is equal to dx over dt. Now for those who don't know, when we say dx over dt, that's basically saying the derivative of the function of x with respect to t. So whatever is on the bottom, that's pretty much what we're taking the derivative of. So in this course, AP Physics C, you're pretty much going to be doing things with respect to time or with respect to x, as you'll see later on. So going on, another thing is, instead of the acceleration equation, we can actually rewrite that as dv over dt. If we actually combine this with what we had from before, that velocity is dx over dt, we actually get this d2x over dt squared, which is basically the second derivative of x over time. Just really quickly, this is actually kind of an interesting thing about calculus, is that this property basically is compiles together. So for example, instead of writing dv divided by dt, I could do d over dt of, and since velocity can be rewritten as dx over dt, this is why we can rewrite it as d squared x over dt squared, because we have two d's multiplied squared. So basically meaning that if I take the derivative of a derivative, I'll get the acceleration. Continuing on, instead of writing j equals ft, I could actually rewrite this as j is the integral of f times dt. basically saying that I have to take the integral of the force with respect to t. Again, that's kind of what this dt is telling us. It's always about what are we doing it with respect to. Instead of writing the work equation as force times distance, we could rewrite it like this. I think at this point we haven't really talked about impulse or work, so this might not make too much sense right now, but what I'm trying to get at is the idea that a lot of the equations that we have, if they include multiplication, that pretty much means that we can turn that into an integral, which is, again, a fancy area. If it's division, we could turn that into a derivative, fancy slope. If you recall, one of the things I had mentioned when we did graphs, I said before that, if you look at your equation and you can do, if you're doing division in the equation, that means you take the slope of that graph. So for example, if we had a graph that's distance versus time, like that, the slope of this would be velocity, because the equation that relates the three has distance divided by time. That's division, that's seen in slope. It's the same idea here, that if there's division, we get a derivative. So this is kind of one of the reasons why I mentioned that it's really useful to kind of remember that derivatives is just a fancy slope and integrals is a fancy area. That if you think about some of the graphs that we've done and you think, okay, would I do a derivative, would I take a slope or an area, that can kind of help you figure out which one you're going to do, derivative or integral. If it's multiplication, it's an area, it's an integral, so on, so on. So I just wanted to point that out, that if you look at any of the equations and you look at pretty much whether or not we're multiplying variables or dividing variables, it turns out that we can rewrite that into derivatives and integrals just by looking at what we're doing. All right. Now this is actually something that you might not have learned in calculus, or at least not in this exact way. So this is going to be new. This should be new for everyone. But one of the things that you might be asked to do is write what's called a differential equation. Basically what this means is, instead of solving the way we normally do, we look and replace the, usually it's the motion equations, acceleration and velocity, with their dx over dt or dx, d2x over dt squared, versions. So a lot of times, I don't know why I said that this is usually, so this is usually used with force equations because it's the only thing that we have where we tend to have things that are acceleration dependent, but also velocity dependent. And you'll see what I mean that for in a second. So I'm going to give you a sample question, and I want to point out that this question is not a typical question. This is actually kind of on the harder end. This is not something that you'd be expected to do, but I just want to kind of give you an idea of what I mean when I say, that we just kind of make a differential equation. So let's say we had a question that looks like this. It says that we have an object and it's experiencing a frictional force, and they give us this equation that the frictional force is negative BV, and that we have an applied force that's given by this function, that apparently the applied force is increasing over time. And they want us to write some differential equation as a function of time. So what I'm going to do is I'm going to start off with the same way that I would solve it without ignoring all these V's and T's, right? And the fact that they want a differential equation. So I start off with my general F net equals ma. We have two forces. We have the applied force and the frictional force. They're going in opposite directions, so I'm going to put the negative in here. Just note that the negative in here is actually already giving me direction. So when I plug this in for the friction, I'm not going to carry over the negative. All right. So what I can then do is just plug in 30T and BV in for the applied force and the friction. I switched the sign so that I did carry in the negative, but again, it doesn't matter. So we end up with this. Now, in a typical physics question, this is pretty much as far as we can go, or AP1 style question, this is as far as we'd be able to go. We'd have to be given information about the acceleration or the velocity. But when we get to the next part, this is how we'd actually incorporate the differential equation. So instead of V, I'm going to plug in dx over dt. And then instead of acceleration, I'd write d2x over dt squared. That's pretty much it. Now, like I said, this is not really a good question. I just want to throw some stuff in here. The questions that you would do as differential equations are much more straightforward than this and are a little bit more on the simpler end. All right. So for those who haven't taken calculus or need a little refresher on calculus, I'm just going to do a very quick rundown of the two main types of things that you need to be able to do. Like I said, you need to be able to do derivatives and integrals of quadratics and of trig functions. So I'm going to focus on the quadratics. Now, for now, I'm calling it quadratic, but this is actually any polynomial. I really probably should have called this a derivative of a polynomial. But as you know, polynomials tend to have the form of, ax squared plus bx plus c, yada, yada, yada. Maybe there's an x cubed term, whatever. So the easiest way to get a derivative is you take the exponents on top of each of these x's and multiply the coefficients by those exponents. Then once you do that, you subtract 1 from each exponent. Like I said, I'm not going to go into the nitty gritty of why we're doing this or what the whole concept behind this is. All you have to know is that a derivative is just the instantaneous slope at any single point along a curve. That's really the definition of it. You just need to know what it ends up meaning. Like I said, it's a fancy slope. So how would this look like for this equation? Well, first, what I need to do is I need to rewrite this quadratic. Again, I'm going to show it to you once. For the most part, you're probably not going to do this ever again because of some of the things that you'll say. So if I rewrite all these terms, the x squared doesn't change, but with this x, I'm actually going to put a 1 in there just to remind myself that this is technically raised to the 1. And even though there is no x term on c, technically I could actually write it like this, x to the 0. You'll see why I'm doing that in a second. Now, as we mentioned, we're going to multiply the coefficients by the exponents. So the a gets multiplied by 2, the b multiplies by 1, and the c gets multiplied by 0. And then I subtract 1 from each exponent. So 2 minus 1, 1 minus 1, and 0 minus 1. So 2 minus 1 is just 1. 1 minus 1 is 0. And I don't really need to worry about this because it's being multiplied by 0, so it drops out. So the derivative, which I'm actually writing as this is actually another way that you can show you're taking a derivative, is by putting a little tick mark above it. So you might actually see, I don't think a lot of questions would have this on the AP, but you might see velocity being rewritten as x to the x prime, x to the first power, or you might see acceleration as x, whoop, messed that one up, x with the 2 ticks to represent a second derivative of x. Just one way of it being shown. But if we took the derivative of this function, I'd end up with 2ax plus b. So that would be my new function. And again, this basically represents the slope at any point along this curve. So if I plug in a 2 here to find a specific point on the curve, I plug in that same point in for x, and I would get whatever the slope of that line that passes, that's tangent to that point. All right. Now the integrals are not that much more difficult. Integrals for the most part can be trickier, but with quadratics, it's actually really straightforward. Basically, you just kind of do the backward steps of what you just did with the derivative. You might actually have learned it in calculus as being called an antiderivative, because that's kind of what it is. It's the opposite of taking the derivative. So in taking the derivative, we multiplied the coefficients by the exponents, then we subtracted 1. We're going to do this backwards. We're going to add 1 to each exponent, and instead of multiplying, we're going to divide by whatever our exponent is. So this quadratic, starting off with this, again, including the zeros and whatever, I add 1 to this exponent, that becomes 3. I divide the a by 3. I add 1 to this exponent to get 2. I divide b by 2. I add 1 to the exponent 0, and I get 1, so I divide c by 1. Then one thing that you might have to do is you're going to have to add in this constant term. I'll mention why in a second, but cleaning this up, we'd end up with this: 1/3 ax cubed plus 1/2 bx squared plus cx plus some constant term c. And this is called a indefinite integral. Now, why do we have to include this constant term c? Well, let me give you a quick little example. Let me do a very quick and easy equation: 2x plus 3. All right. So this is my function. Oh, sorry. This is my function. And if I take the derivative of this function, I'd end up with 2. All right, easy enough. Let me change the function so that it's 2x plus 6. Well, if I take the derivative of this, I get, once again, I get 2. No matter what this constant term is, I end up getting the same derivative. So basically what it kind of means is that when we take an integral of something, we don't really know what that constant term was because it got, deleted. It was multiplied by 0, and technically any number can be multiplied by 0. Usually the way that they're going to work this in, because you might actually have to figure out what C is they'll tell you whatever the initial value was. This ends up being your initial value. So if this function is supposed to be velocity as a function of time, then this c term actually ends up being your initial velocity. So they would tell you, initially the object was traveling at blank speed. All right. Now there is another type of integral called a definite integral, or what you're going to have to do here is they'll tell you 2 points. And essentially what you're going to do is plug those numbers in for whatever x or t is, and then subtract them. Essentially, if you remember, I keep mentioning that integral is like doing an area. If I asked you to take the area under this graph from between 2 and 4, you should know that one of the ways that you could do this is by taking the area under the curve. So you're going, this is a triangle shape, so I could do half base times height, where this is for 4, so 1/2 of 4 times 60. And then I could subtract it by this smaller area, the one that I'm not actually using, 1/2 2 times 30. And that's how I can find the area. That's pretty much the idea that you're doing. You get your equation for how you find the area under your curve, the integral equation. Then you just plug in the values at the high end, plug in the values at the low end, subtract them, bada bing, bada boom. And there's your area. All right. So let's do some practice questions. So try this yourself. If you're new, that's fine. Just, do what you can. So pause video, work stuff. We'll go over in a second. All right. So these are all going to be examples of multiple choice questions that you would see with calculus. So here they give us this acceleration equation as a function based off a function of time. So it's changing over time. And it wants us to know, it says that when the object starts from rest and has a position that are 0, when t equals 0. So they're telling us that the initial velocity and the initial position are both 0. So that's going to make our lives a little bit easier. And we want to know, where is it located at t equals 2 seconds. So I'm looking for the x at t equals 2. So what I'm going to have to do is I'm going to have to take the integral of this 2 times. So if you recall, velocity, the delta v is equal to at. Like I said, this is multiplication. So what I can do is I can realize that I could just take the integral of this acceleration equation, and that will get me my velocity equation. So the integral of the acceleration with respect to time is just the integral of 12t dt. So again, I'm looking at time, that's my variable. So the exponent is a 1 on that. I'm going to add 1 to it to get 2. Going to have to divide the coefficient by 2. I add in this c term. 12 divided by 2 is 6. So my velocity equation is 6t squared plus c. Now, I know for a fact, because of here, that the initial velocity is 0. So just testing this out, if I put 0 in for my t, and I say that velocity is 0, I get that c has to be 0. So again, the idea is that my initial velocity is 0. I could have realized that and just dropped it off right from the get-go. Once you have more experience, it becomes a lot quicker to do these integrals and derivatives. Now, I don't want the velocity, I want position. So again, keeping that like same mentality, I have to take an integral again. Again, if you needed to remember or if you forgot, you could just realize that, oh, the equation for position, if we took that same average speed equation, is velocity times time. That can be turned into an integral because it's a multiplication. So integral of velocity with respect to time, that's the integral of 6t squared dt. Once again, I add 1 to this exponent, gets me 3. Divide the 6 by 3. So I get 1/3 of 6t cubed plus c. That just simplifies to 2t cubed plus c. Once again, they told me that t equals 0, my position 0. So I plug that in. I get c is equal to 0 once again. Now, to actually answer the question, I want to know where is it located at t equals 2 seconds. I put in 2 for t, so that's 2 times 2 cubed, which is 16 meters. And that's it. So that's what the multiple choice questions kind of look like. All right, here's another one. Pause video, works up. We'll go over in a second. All right, so here they give us a velocity equation, and they want us to figure out the acceleration at a certain time and the displacement between two different times. So let's start with the acceleration. Again, we know that the acceleration is velocity divided by time, which is just a derivative. So it's the derivative of velocity with respect to time. Notice how the terminology kind of is very similar. Now, I don't like using the equation format in here only because I can't really transfer it later on. But I just want to point out that this is division, d divided by dt. And in fact, what I can do is I can pull out the v, so it's d over dt of the velocity equation. So this is kind of how it's written when you are taking the derivative of something. So d over dt of the velocity function, 4 plus 0.5 t squared. So again, I know that the 4 is being multiplied by a 0. That's going to end up dropping out. The 2 multiplies by the 0.5. I subtract 1 from that exponent. So I get 2 times 0.5 is 1. T to the 1 is just t. So I end up just getting t. So plugging in 2 seconds, I end up getting that my acceleration is 2 meters per second squared. Moving on to part B. Let's see, we end up having, they want it between 1 and 6 seconds. So again, I remember that the integral of the velocity term, or the velocity function, is position. So I'm going to do that. Now, this is just a formatting issue. Because I'm not doing an indefinite integral, I'm doing a defined integral where I have a start and end point. I'm actually going to, this curved S is actually the integral symbol. I'm going to put a 1 and a 6 there to represent my initial value and my final value. Again, this is just how it's, the way it's written. So once again, I'm taking the integral of this with respect to time. So the 4 is easy enough because there is no t on it. It just gets a t. That's it. Here, I end up having to add 1 to this exponent to get 3, divide the 0.5 by 3, and I end up getting 4t plus 1 over 6 t cubed plus some constant term. Now, you're going to notice is that when we do a definite integral, the constant term doesn't matter. And then once again, just the way it's formatted, we put a little line here and put 6 and 1 to remind ourselves that we have to evaluate this at the final value of 6 and the initial value of 1. So I plug in the values. I plug in 6 in for time. So it gets 4 times 6 plus 1 over 6 times 6 cubed plus some constant minus the initial value. So 4 times 1 plus 1 over 6, 1, blah, blah, blah. So this is going to simplify to 24 plus 36 plus c minus 4 minus 1, 6 minus c. You can already see why the constant term doesn't matter because it always drops out. So a lot of times when you're doing the definite integral, you don't need to worry about the c. You just really worry about this part in particular. So cleaning that up, we end up getting 56 minus 1 over 6, which is 55.83 meters as my final displacement. All right, pause video, works out. I'm going to go in a second. All right, so here's a change, a switch of what we were doing just now. So here, it doesn't seem like there's going to be a very quick comparison to this. But if you recall, one thing that you should be doing is trying to think about what links force with, position or kinematics essentially, and we know that that means acceleration. So if I can take this equation, turn it into an acceleration equation, then I can compare it to my net force equation, since I know net force equals mass times acceleration. So I take that position function, I take the partial derivative, not partial, I take the derivative of it with respect to time. So d over dt of this position equation. So each of these terms, I multiply the coefficient by the exponents. So 3 times t squared, 2 times 6 t to the first, and then just 9. So I end up getting this. Acceleration is just doing the derivative one more time. So 2 times 3 gets me 6. I take 1 away from the t, so it just becomes t. There's nothing, the exponent's 1, so it just becomes minus 12. And the 9 drops out because it's a constant now. So now I have 6t minus 12. Now what I can do is, they said that they want to know what time when the force is equal to 0. So since the force is equal to 0, I know that the acceleration has to equal 0. So I said this equation, 6t minus 12 equal to 0, move the 12 over, divide by 6, I end up getting 2 seconds. So at 2 seconds, I end up getting 0 acceleration and 0 force. All right. Here's the next one. Pause video, work itself, and go over in a second. All right, so this is a little bit more complex than some of the differential equations that you might see. This was actually the only one that I could find on such short notice, but you'll notice that it's still fairly straightforward, that you'll see when I go over it that it is pretty easy. So there's actually a few ways that I can simplify this before I continue. So one thing I can do is I can look at these terms, and I'm not really going to pay too much attention to it. I'm just going to pay attention to what's on these integral bars. So if you look on this one, 0 and v, and then on the right of it is dv and a v term. If I look over here, 0 and t, and then it's dt. When you're taking an integral of something and you have it and you're with respect to time, these terms have to be time values. So A is a possible solution because I have it matching, but if you look at B, it doesn't match. It's got a dv here, but it's got time values. That doesn't make sense. If I took the integral of this with respect to velocity, there would be no time for me to plug in. So B actually can't be an answer. I can keep this going, and I can also cross out E for pretty much a very similar reason, that 0 to V, but it's with respect to time, 0 to T with respect to V. That doesn't make sense. All right. Now let's go back to the actual question. So they're telling us that there's a lot of forces. So they're talking about forces. They saying that they want us to find the velocity as a function of time. They're giving us the object being dropped from rest and feeling this resistive force. So it's a force question. I'm going to do what I normally do, draw an FBD. So I have my force due to gravity pulling down. I have the resistive force, which is just air friction pulling up, and I'm accelerating downward. So what I'm going to do is I'm going to start the same way that I always do. F net equals ma. So Fg minus that frictional force. I'm going to plug in mg for the force of gravity, kv for the frictional force, and I have ma here. So this is pretty much as far as we can get using general physics, AP1. Now is where we turn into the differential equation. What we're going to do is, since I wanted to find the velocity as a function of time, I'm not going to touch this v. I'm only going to touch the acceleration. I'm going to replace the acceleration with dv over dt, right? So now this becomes mg minus kv equals m dv over dt. I'm doing this so that every single term is, or every single motion term, I should say, x, v, and a are v dependent. So this is now, this is a constant. It's not, dependent on velocity. This is already dependent on velocity, but now I'm turning the acceleration to be dependent on velocity. All right. Now what I have to do is I have to get like terms together. So I have a dv on the right hand side. I want to actually move this to where the dv is. And similarly, I want to move the dt to the other side. So what I did it kind of backwards. You'll see why I did that in a second, but I moved the dv over to the mg, so mg minus kv divided by dv, and then on the right hand side I'm left with m over dt. When you take an integral, whatever term you have, you basically have to have one dv term or dx or dt. All the terms that are on that side have to be in that those measurements, those variables. So everything on this left-hand side is v. The right-hand side, doesn't have a time, which is fine, but I end up with this. I can't have the dv's and dt on the bottom though. If I take an integral, it has to be on the top. So I'm going to actually flip both sides. So I have dv over mg minus kv equals dt over m. And from here, you can already see which equation I'm going to be doing. My solution is going to be A. And that's it. Like I said, this is probably the toughest differential equation that you would see. Most of the time, you're not even going to solve differential equations. You're just going to be asked to set it up, and then that's it. All right. And like I said, you start off with your force equation, then you plug in either dv over dt for A, or maybe it's d2x over dt squared in for A. Whatever it is, you plug that in, and then you pretty much try to clean it up a bit. It's honestly not that many questions. I would say of the 7 questions that I saw on some of the practice tests, there was really only one question that was, make a differential equation. The practice test that you have on Canvas is a much simpler version of this. All right, I just want to quickly run through the trig functions. So these are a little bit trickier since they would normally require some memorization. So let's say that we have this function, the function of time of 2 sine 5t. We want to know what the derivative is. First off, it actually starts off very similar to the quadratics, but instead of taking the exponent on the t and then multiplying the coefficient, we're going to take this inner term, find the derivative of it, and multiply it by the front. So here we have a 5t here. So if I take the derivative of this with respect to time, there's a 1 here. I multiply the coefficient by 1, subtract 1. This just becomes 5. So what I'm going to end up doing is multiplying the coefficient by 5, and I get this. However, this isn't the full story because it turns out this term has to now change. So I'm not done yet. Since we're using sine, I need to remember that the derivative of sine is actually cosine. So what I'm going to do is, when I multiply the front term by 5, I'm actually going to flip the sine and turn it to cosine. So my actual derivative of 2 sine 5t is now 10 cosine 5t. That's it. Really quickly, I don't think it's going to pop up, but let's say this was instead 5t squared. Using your amazing quadratic skills, the derivative of this term is going to be 10t, because I multiply the coefficient by 2, subtract 1 from it, so it becomes 10t. So this would actually become 10 times 2, which would be 20t 5t cosine 5t squared. So I just want to remind you that you're taking whatever this inner term is and multiplying by the coefficient. However, I think the way a lot of the questions are going to be set up, you probably wouldn't be seeing this. Most of the times would only be a single time. Now, this is kind of why I said that it requires a little bit of memorization, because the thing you have to realize is that while the derivative of sine is cosine, it does turn out that the derivative of cosine is sine, but it's actually negative sine. So if I took the derivative of this one more time, I would once again multiply the coefficient by 5, turn the cosine to negative sine, and now I'd end up with negative 50 sine 5t. So it's something that you kind of have to remember. We'll do this question real quick. So pause video, work self, we'll go over in a second. Now, we haven't talked about these periodic equations yet in AP Physics 1. This is actually the second to last unit. So if you don't know how to get the equation, that's fine. What I recommend is, watch what the equation is that I'm going to write up, and then see if you can find the velocity. So this is the position graph. Now the way trig functions are written in this class, at least, is that they're always going to be written in this form. A is the amplitude, 2 pi is just a standard term, 2 pi t, and then this is the period. So the time it takes for one full cycle. So in this case, my amplitude is 4 because it goes between 4 and negative 4. I have the 2 pi t, and then the period is 2 seconds. This is one full cosine curve. So this would be 4 cosine of 2 pi t over 2. The 2's drop out, and I'm left with pi t. So 4 cosine pi t. I want the velocity, so that's the derivative of position. So I have to take the derivative of this with respect to time. This basically just pulls out a pi. The cosine turns into negative sine. The pi t still remains the same in the beginning. So this just becomes negative 4 pi sine pi t. Now, I know what you're probably thinking about. This might be an issue having to memorize this. I haven't really done calculus. I'm not doing it, or, I'm not really good at trig. Don't worry, the reference table actually has everything covered. There is a section in the APC reference table that has all the calculus terms. Now, this is a lot of terms. You don't really need to worry about it, but you'll see right here, these are the derivatives of sine and cosine. This is the derivative of a polynomial or quadratic. That, again, if you have x to some exponent, you just multiply the coefficient by the exponent, subtract 1 to the exponent, and then here are your integrals. Kind of cut that off. So integrals of the quadratic or polynomial and integrals of the trig function. Now I know what you might be noticing. You're seeing these terms, e function and ln, and you might be thinking, wait, why didn't you go over that? Don't worry about it. If you know it, that's good. If you don't, whatever. Honestly, it rarely pops up. Most of the calculus that you're going to be seeing, which, like I said, is already about less than a third of the test. Actually, it's closer, less than a quarter of the test is going to include calculus. So most of that is actually going to be quadratic stuff or polynomial stuff and some trig functions. Having to do an e function or an ln function isn't really going to be the most important part, essentially. So don't worry too much about it is all I'd have to say. Maybe if you end up being really good at doing these basic derivatives and integrals, then you can kind of brush up and learn about how to do an e function derivative or how to do an ln. They're not that crazy. You might also see some other things on here. Again, don't really worry about it. I don't think they're going to pop up for this. This AP reference table is actually meant for both AP Physics C Mechanics and AP Physics C E&M. And I believe E&M does use a little bit more of these terms. So that might be why they're included. All right. And that's basically it. Now, there's a few other things I do need to go over with, what's included, what's different about the AP Physics C versus the AP Physics 1, but I just wanted to leave it off with that. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.